So welcome to the second class of the course. The last class we have briefly introduced the microstructural features, then the potential energy between the atoms, and also we have briefly gone through the history of towards the development of field electron emission microscope by Erwin W. Mueller. And now in this class we will proceed further towards the field ionization microscope. In the next set of experiments, what Mueller did is, instead of applying a negative potential at the tip, he has applied a very high positive potential at the tip. Okay, and he has also introduced gas around the tip under a very high vacuum. Fine. So these gas he used, it can be either argon, correct. So this introduction of the gas, so the atmosphere is a typically gas, and he has applied a very high positive potential. Due to this positive potential, there will be a ionization of the gas has taken place, due to which these ions which are positive and which are positive in charge, and due to the high potential there will be a very high electric field lines, and these positive charged gas ions will accelerate along these field lines. Fine. And he has kept one fluorescent screen, and these positive gas ions which are accelerated hits to the fluorescent screen, and what you are seeing here, it is an image which is recorded when these positive ions are hitting to the fluorescent screen. And here strikingly you can see that each dot corresponds to one atom. Okay, so with this what he has done is, he actually imaged the atoms. First time he has imaged the atoms with this reverse by reversing the potential on the application of the on the tip. Fine. Okay, so as I told you, so how it was developed. So Professor Mueller has one student who is an Indian student. His name was Kanwar Bahadur. Correct. He was a PhD student who was working during that time, and this was the first time where first image was recorded in 1955. Okay, on October 11, 1955. They used a tungsten tip which is 110 oriented. Okay, and as I told you, they injected the gas atoms. They kept very high potential of positive on the tip, so that due to this large potential due to the large potential, these gas get ionized, correct. And due to the potential there will be an electric field, and along this electric field these gas ions are accelerated and hit to the fluorescent screen. Fine. And they use the gas hydrogen. So what they called is this called as a imaging gas. This is called imaging gas, that carries information about the position of the atoms on the sample lattice, correct. So now what was the role of Kanwar Bahadur? So actually these experiments they were performing at room temperature, at a very high vacuum, and as you know, at room temperature the atomic vibrations are very high. Fine. And also the needle was not sharp enough. They were not able to, it was around 100 nanometers. Okay, so one day Kanwar, what he did is, he suggested Mueller that we can cool the specimen to a liquid nitrogen temperature, and also incidentally what happened, he has made the sharp need of 20 nanometers, which is much less than the 100 nanometers, correct. These two experiments led to this image where you can see the actually the resolved atoms at each dot corresponds to one atom. Fine. So this is how in 1950 so they published a paper in 1956 about this technique where they called it as a field ion microscope. because we are ionizing the imaging gas, and these gas ions are accelerated towards the fluorescent screen or towards the phosphor screen, where these can be recorded as the individual atoms can be recorded on the image. We will come to details about this particular image, how these are recorded and how these bright intensities are actually related to the atoms. Okay, and here in the right side you can see an image of Bahadur during a conference, which was related to the development of field ion microscopy. Okay, so in the later after this experiment, how to identify the atoms. Now in the previous slide, what I have shown the bright spots, and these spots corresponds to atoms. Now you have to recognize these atoms, correct? So which element is present, what is the chemistry, what is the chemical identity of these bright spots. So in 1967, Mueller's student, whose name was John Panitz, he was a PhD student, and what he has done is he has attached a time of flight spectrometer, correct? He has attached a time of flight spectrometer for the field ion microscope, and with this time of flight spectrometer, he has actually identified the nature of that particular atom. Fine. What is time of flight spectrometer? It means that it is related to the time of flight of the ions which are traveling from the tip to the fluorescent screen. Fine. And by measuring this time of flight, actually you can identify what type of species is present in the microscope, through the microscope, correct? And this was the instrument which he developed, and he was the student, PhD student, with Mueller. And the main issue with this technique is the detection. So in an hour only 10 atoms were detected, correct? And also 1 nanometer field of view. It means that the region which is under field evaporation. Okay, so the field of view was very small, and the time taking for individual atom to record it was around 10 atoms per hour. So this was the major issue with the first pulse. So what we call it, what they called is pulsed field ion evaporation, and 1 ion at a time. Fine. So in the later, this was developed in 1967. In 1972, there was a development related to spherical microchannel plate amplifiers, correct? So it means that 1 ion striking to this amplifier will generate a large amount of secondary ions or secondary electrons, which corresponds to which can increase the detection efficiency, detectability. So with this, in 1972, they were able to generate 3D data with 2D maps. Okay, but the issue with this type of technique is you can only record single atom type at a time. It means that if you have an atom probe tip, which consists of aluminum and copper, so at the top part you can actually at a time you can only record either copper or detect or only aluminum. Once copper is detected, then later you can detect aluminum. Fine. So it was only the disadvantage was single atom type at a time. Later in 1988, there was a drastic change where position sensitive detectors were developed. Okay, position sensitive detector, and it was termed as POS atom probe. POS atom probe. Okay, position sensitive atom probe, which was in 1980s was developed by Godfrey and Smith, and this was published in a scientific instrument journal where they used position sensitive detectors, and the problem of single atom time at a time was solved. Okay, and also the field of view was improved to up to 15 nanometers field of view. Fine. It means that in a particular tip from this region, actually you can record or you can detect both aluminum and copper at a time. Fine. So this was the development in 1988. Later in 1993, a professor from Japan, where Professor Nishikawa, what he has done is he kept a funnel shaped electrode just ahead of the tip. So these sharp needles, you can consider them as samples or the specimens, the needles. And what he has done is he has kept a small electrode just near to the tip. So assume there's an atom probe tip, and he has kept a one hollow funnel shaped electrode in the position. Okay, and he has applied a very high potential. What is the effect of this electrode? Actually, in this, your electric field generated around the tip can be more concentrated. Correct. So your and the fraction of which would pass through. So these ions which are generated, so your efficiency or the detectability of these ions are much increased. Means the number of atoms detection are with very less time was possible by introducing this electrode just ahead of the atom probe tip. Okay, then in 2001, based on this design, similar design, okay, so what Thomas Kelly and his colleagues, what they have developed is the local electrode atom probe. Okay, so this idea was came from the work by Nishikawa, where they used a local electrode just near to the atom probe tip, and this, due to which the electric field lines just ahead of the atom probe tip, it got concentrated, and the field of view got improved much higher, up to 150 nanometers. Okay, and this is a one typical modern atom probe which we call as a LEAP, LEAP, local electrode atom probe. And this it was named as 3000 XHR, 3000 XHR, correct. Very high data collection, up to 10 raised to the power 7 atoms per hour. Also there is a reduction in energy spread, which means that the mass resolution got improved very effectively by this thing. So here you can see the schematic of this setup, where you can see this is the microtip specimen, similar to the specimens which was shown by Nishikawa, and this is called local electrode. This is called local electrode, correct. And the voltage was applied between this local electrode and the needle specimen, very high voltage, positive voltage and negative voltage here, due to which the electric field lines all are concentrated. That's why you will so that the data collection of a large amount of atoms was possible by this setup. Okay, and in this setup I will come to the construction of this local electrode atom probe later. And here this is the imaging detector. This is called imaging detector, and I will tell about more on this, how this imaging detector is also increased the development on the related to the imaging detector, which lead to the collection of high number of atoms per unit time. Okay, so parallelly, when I told about the FEEM, okay, field emission electron microscope, FEEM, correct, by which uses electrons for imaging purpose. Okay, when Mueller was working on this, parallelly in the same institute there was a professor called Max Knoll, and he had a student whose name was Ernst Ruska. Actually he was working on a new instrument based on this FEM, correct, and which is called electron microscope. for which he got a Nobel Prize in Physics in 1986. So this was the first microscope, electron microscope, which was designed by the Ernst Ruska, who was a student of Professor Max Knoll. Okay, so it was designed in 1931, and in the same university Mueller was working with on this FEM microscope. Okay, so Mueller, the only difference is Mueller what he was using is he was using FEM technique for microscopy, but here here Ernst Ruska, what he did is he used electrons. He used the electrons to create images by interacting them with the samples. Okay, so this was the difference between the two, where they were working together at the same time. They were working during 1930s. So here there are two cases, the first and the second case. This is related to FEEM, and this is related to FIM. This is related to FIM, field ionization microscopy. Fine. So, and you can see that comparison of the images between these two. Here these electron there's a bright diffused spots which corresponds to the electrons hitting to the screen, but here actually due to the ionization atom, gas atoms, you can actually resolve individual atoms. The bright spots corresponds to individual atoms. Fine. So with this basic we will further go towards the microscope. So as we see that this is related to the resolving power. Fine. Resolving power, I will come to the definition of resolution later. So this is from the macro to the nanoscale. Fine. So we can see that at the centimeter and the millimeter scale we can actually see by the naked eye the features, while it might be the hair. Okay, and we use optical microscope, electron microscopes, okay, based on the resolution, based on the resolving power what we want. Okay, so optical microscopes, it uses light which is having a very higher wavelength. Okay, so based on the wavelength you can actually resolve the techniques, resolve the features which are required. Fine. And if you use the electrons as a source, then you can resolve, actually these electrons are accelerated towards the sample at a very high voltage, and this particular voltage is directly related. Higher is the voltage, smaller is the lambda. Lambda means smaller is the wavelength, and smaller is the wavelength, and then the resolving power will be very high. Fine. So this is how a complete spectrum of from macro to nanoscale, and how this evolved with time. Okay, so I am showing you an SEM image. Okay, this is an electron image, correct, and as you can see in this image there is a certain related to the gray contrast. There is a gray contrast, there is a dark contrast, and still there are darker contrast. Fine. And you can easily see the dark contrast across these boundaries, correct. These are called grain boundaries. Fine. These are called grain boundaries, and you can see somewhere you can see the twin boundaries also. Fine. So this is the contrast. This is an electron image, secondary electron image, where it is recorded in an SEM, where you can see the contrast related to the grain structure. Now, so as I told you before, this particular structure, the grain structure, is developed by this particular root. Fine. So it will form a nucleus, correct. After formation of nuclei, the nucleus will grow at different positions, position 1, 2, 3, 4, and this develops to a grain structure which we are seeing it. As also described in the previous class, this one particular grain has a one particular crystal structure. Correct? One particular grain has a one particular crystal structure, and this crystal structure is nothing but a repetition of the unit cell. Now, if I prepare a sharp needle with this particular region only, if I am preparing a sharp needle which is having a radius of curvature of around 100 nanometers, less than 100 nanometers, correct? So this is a particular needle. We will come to the sample preparation later, but now consider this is a sharp needle which is having a radius of curvature less than 100 nanometers, or it is mostly around 50 nanometers. I am talking about radius, correct? This is a very sharp needle which is made from this particular grain. Fine. If you go further, if you go further on and that particular tip, you can see that this tip consists of these blue spheres, correct? And these blue spheres are nothing but atoms which are arranged in a periodic fashion, correct? So now I'll connect all these things together to understand this, correct? And these blue color spheres are nothing but the atoms which are arranged in a periodic fashion, correct? If you zoom this particular tip, you can see that these atoms are having a certain orientation in this direction. It might be 111 orientation, and you can see that this is your first plane, this is your second plane, this is your third plane. So I am talking about in two dimension, correct? I am talking about like this, interplane. So between these two planes you can see there is a step, okay? So you will have, so if you zoom out, you will have a one plane, there is a step, another plane, there is a step. So you will have a ledge. So this is called ledge or the terrace, or we can call as a terrace. Fine. This is the zoomed out region of that particular tip. Fine. If you see at the atomic level, at still magnification, you can see what I shown here at the terrace. These are called terraces, correct? These are called terraces. What is the importance of these terraces? So I'll come in the next next few minutes. So if this particular tip, if you see in this direction, in the z direction, from means the top view. The top view of this is this top view. Fine. And if you see that, you can see that these atoms are arranged in a certain crystallographic direction, okay? And this particular orientation is 001, okay? So you can see the cubic symmetry. Fine. So, and if you zoom in more, you can see that these atoms are actually in the cubic direction. You can see here, this is the atom, and this region between these two is the terrace, correct? So this is another plane, again terrace. This is another plane, this is again terrace. So this you can see the complete crystallographic nature of the atomic distribution or a position of the atoms at the tip surface, at the top tip surface, okay? And if you see the cross section of this particular image, you can see that I can assume this is a big this is the tip, fine, and this is the top part of the tip, and you can see that I have shown you that these terraces. So this is one particular plane, there is a terrace, there is a terrace, then another plane. The edges, where the edges of these terraces are prone to very high electric field. When you apply a field, then the electric field around these edges will be much higher than the electric field concentration at these flat faces, okay? This is related to your radius of curvature. As I told you, F is equals to voltage by R, correct? the voltage applied, and the field above field is inversely proportional to the R. So due to this terrace effect, or due to this sharp point, the field around this region, at this region, will be very high as compared to the flat surface. This will have a direct consequence of the field ion image which we have gathered it. Okay, so now you remember that we are actually seeing this atomic structure on the tip surface, and these are called terraces, which are very important consequence for the field ion images. Okay, how it is related? So what Mueller has done is, this is in 1951, this is published in 1951, the instrument. Okay, so that instrument, it is called field ionization microscopy. Fine. So what he has done is, this is the liquid nitrogen to cool the tip. Fine. And this is your atom, this is your tip. If you zoom out, it will look as a very sharp needle. Fine. Now he has introduced a gas. This is the gas inlet. He has introduced the gas, hydrogen. You can use also argon. Okay, so this gas, when you apply a very high voltage between the tip, positive voltage, and this is a this is the channel plate where the for the detection. Okay, if you apply a very high voltage between the channel plate and the atom probe tip, what will happen? There will be a high field ionization of the gas which is injected, which is called imaging gas. Ionization of the imaging gas. And due to the field developed by the potential applied, the electric field lines will be in this direction. Okay, and these gas ions will accelerate towards these field lines, and it will hit to the channel plate. Now this in the right side, this is the schematic, and I am showing you one image here, which is called a field ion image. Fine. Now in the previous slide, if you remember, in the previous slide, what we see here is this particular top view. Okay, and after application of the field potential, the gas atoms, the imaging gas atoms, what will happen is, the imaging gas atoms will get ionized much faster in these regions, because you are injecting a gas, correct? So these gas atoms gets ionized faster, and so they will accelerate at a very much faster than the or they accelerate at a very less time, okay, than the atoms which are gas atoms which are present on the flat surface. Fine. Due to which you will develop these spherical things, and each sphere actually corresponds to a certain crystallographic orientation. So the arrangement, so if you zoom out this particular region, or if this zoom out, you will get atoms which are arranged in a circular fashion, correct? And this circular fashion atoms, it is nothing but the gaseous atoms which are field evaporated from the terraces, and the symmetry of these terraces and the position of these terraces, or the symmetry of these terraces, shows the crystallography or the orientation of that particular region or the tip. Fine. So now you understand that how the terraces, which we have schematically shown, is related to the bright spots which are recorded in the field ion image. Fine. So, and you can see that these all bright spots corresponds to single atoms which are from which are the image, which is the image of the surface atoms of the particular tip. Okay, so what we call is a film provides the atomic resolution imaging of the surface of the specimen. An imaging gas we can use helium, neon, argon. Okay, it is introduced around the highly positive charge sharp needle. Then the electric field around the apex, as I told you, around the apex of the specimen is of the order of 10 raised to the power 10 volt per meter. It means that 10 raised to 10, it means that 10 volt per nanometer. Such a high electric field is generated when you apply a voltage of that with sharp needle. Fine. Then the image that is formed is by the impact of the gas ions, which is called imaging gas, on the phosphor screen maps, and it shows the distribution of electric field at the surface. Fine. It is nothing but you are imaging actually the distribution of electric field around the tip. As I told you, these are the terraces. Fine. And the distribution of electric field is different at the flat surface and at the terraces, and actually in your film image you are seeing that distribution directly. Okay, and it is intrinsically related to the local topography of the tip. This is how you can resolve actually the atoms by the field ionization, field ion microscopy. So here one more important point is the specimen is maintained at extremely low temperature. Okay, and to optimize the spatial resolution, because at room temperature the atoms vibrations are very high, so they are kept at very low temperature, and the voltage is applied is high enough to provide direct imaging of the individual surface atoms. Correct. So that the the voltage is applied in such a way that the imaging gas which is used should get ionized. Fine, should get ionized. We will come to the ionization in the coming slides. Fine. So for a non-flat surface, as I explained you, for a non-flat surface the protruding atoms are subject to a greater charge. Okay, so this particular region we call it as a protruded atoms. Okay, and the electric field distribution along this and electric field distribution here is totally different. Here it is more intense and more concentrated than the flat surface. So the electric field at the surface is directly proportional to the charge density. It is higher around these local protrusions. So, and in the case of atomically smooth curved surfaces, these protrusions corresponds to the edges of the atomic terraces. So what we call as a atomic terraces. Then by imaging the distribution of field intensity, so there is an electric field around the tip. By imaging the distribution of field intensity at the surface, the field ion microscope provides an atomically resolved image of the surface itself. So this particular image at the right side is actually the image of the electric field distribution across the tip, which directly related to your local protrusions, which are nothing but the atomic terraces, and which gives the crystallographic information also. Correct. So this is how Mueller has developed this technique in 1951. So with this I will end the second class here. Now I have given you a brief overview of from the field emission electron microscope towards field ion microscopy. Now in the next class what we do is we will discuss about a basic physics related to field ionization. Fine. So we will cover the basic physics related to the field ionization, which is very important to understand the electric field distribution across the atom tip or the needle specimen.